so you're not too far from home, right? Rianne, did you have yours? You just need to get them? Okay. All right, so I suggest getting those, and you might have, if you got a separate notebook, you might even want to put pages in right along with your principles, however you want to do it, but I think it'd be a good idea, because I'm going to spend some time today rehashing some of the principles, and then we're going to apply a little more quantitative analysis to the topic of elasticities. And then we'll be pretty much done with chapter 2 already. Okay, questions? So, we did supply and demand shifters and the basics, the law of demand, and we've did an example using equations. What kind of special name do we give this demand curve when it's written in this space with P here and Q here? Inverse. So it's the inverse demand curve. Why do we think of it as the inverse demand instead of just the demand? The X and Y, talk to me in terms of the economics though of what's going on, of why we say that, well, it's kind of inverted in a way.
In terms of price rather than quantity.
Yeah, so quantity is the dependent variable. In other words, always think about the choice variable in these constrained optimization problems. That's really what we're doing all the time when we get to utility, when we get to cost, when we get to profits. It's called a constrained optimization problem. And the choice variable is the Q. You are choosing how much energy drink to buy, given that the price of the energy drink is $3. So at $3, you'll buy this amount. That's the dependent variable. And so when we write it this way, because of the traditional math of the independent and dependent variables being flip-flopped, we call this the inverse demand curve. So that's kind of helpful to just remember that as we work through some problems. So also make sure you're very comfortable with the details. Oops, there, I guess I'm inverting. I'm going back to the regular one here. Of home base. So again, this is kind of my terminology, but it always gives us an anchoring point to come back to. And one of the things that makes an impact on the market and the sensitivity of price and quantity changes, I brought the golf clubs today so you know where this is going, is the steepness or flatness of the curves. So depending on what this looks like, it's going to impact the effect of, let's say, an increase in supply. What is the change in the quantity demanded? Well, if this demand curve is more or less elastic when I draw it like this, more or less elastic, less elastic, so more inelastic. Again, my little trick is to, as the curves become steeper, they start to look like an I, or inelastic. And so as we become steeper, now you can see that that equilibrium point for Q1 would be falling right down here. And so there'd be a lot less of a change. And the same holds true for supply and its relative elasticity. Okay, so the elasticity of demand and some texts use it differently, and I didn't look that carefully at this one. A lot of times it's the price elasticity or the own price elasticity. And give a quick check here. I think they just call the price elasticity, don't they? Okay. So the price elasticity, the elasticity demand or the price elasticity, I guess I'll go ahead and put, where'd you see that on? Page 43? Oh, that's too far back. Okay. There we go. Good. So page 4, let's just, I guess, sneak in. I'll keep consistent with the text here. The price elasticity of demand. And luckily, the author uses a very similar notation to what I did. He puts a capital E. I've just kind of do this little summation. E superscript D. So the price elasticity of demand is the, let's define it first before we do the formula. It is simply a number that shows the responsiveness of quantity demanded to a price change. I guess since I opened it, what did they put here? The percentage change of quantity resulted from a 1% change. So the elasticity ends up being a unitless number. There are no units to it. It just is what it is because it's the ratio of two percentages. And one little trick that we do, and your textbook even kind of wraps this into the definition. In fact, might as well. If you put that number over 1, you get an easy interpretation of the elasticity of demand. And so I'll show that in a second here, but you're basically getting a number. Well, in fact, let's just jump the chase since this is intermediate. I'm going to come back around to it, but let's say, suppose that the elasticity of demand is equal to 1.35. So the trick that I'm saying is to take whatever that number, the elasticity of demand is 1.35. If you put that over 1, then you get your interpretation of a 1% increase in price leads to a 1.35% decrease in quantity demanded. And so our formula for the elasticity of demand is the ratio of the percentage change in quantity demanded over the percentage change in price. Now this is where we're going to take things slightly different than what we did in principles class. Remember doing the average of the two things when we calculated it? So when we went from, if price was $4 and P1 was $3, and this went up from 100 to 120, when we calculated the percentage change, we averaged these two out, which was a little bit of a different innovation dealing with whether it was a price increase or price decrease. Now we got our big boy or big girl pants on, and we would normally be doing this with a derivative. So that distance would be infinitely small and represented with just a point on the curve. And so that change thing, it's kind of irrelevant doing the average of the two like we did before. It's really just a point estimate along that demand curve because we're going to take really small changes. So the way the textbook treats it here is without using the calculus is kind of going back to the old percentage change, the new number minus the old number divided by the old number. But we're taking a really small change, so the new number and the old number is really right next to each other anyway, so it doesn't matter. And so from that, we can generically write this formula as the change in quantity divided by the point at which we're estimating it, that quantity. New number minus the old number divided by the old number, but they're close to being the same anyway. Right? Divided by the percentage change in the price. Same thing going on there. And so now our Q and our P represent a specific point along the linear demand curve where we're estimating it. Yeah, and go ahead and if you want to just put a 0 there just to kind of remember that it's 1 point along the demand curve. So when we go back to do this formula now, we're going to find it at this point, and we'd be using 4 and 100 when we go back to do it. Okay? So this gives us a little bit different twist here too. If we take this formula and rearrange the terms, kind of multiply the top times the bottom, we get the change in quantity. I'm going to do this in 2 steps here. Divided by the change in price times the point estimate along the demand curve. Now, change in Q over change in P is close to being what over here? What's the slope of this line? What's the slope of the demand curve currently? I'm not even looking for a real number, although we could calculate it, I guess, here. But yeah, so change in price over change in quantity, right? Rise over run. We don't quite have that here. We've got change in quantity over change in price. So we can re-express that as 1 over the change in price over the change in quantity times that point estimate. And the reason we did that is it gives us this little formula. 1 over the slope of the inverse demand curve over the slope of the inverse demand curve times the point estimate. And so that kind of is helpful now if we look at a function in slope-intercept form. If we don't have our graphing goggles on and all we're looking at is the demand curve in functional form, and we know slope-intercept form, boom, I got the slope. 1 over the slope times a couple prices and quantity combinations that are on that function gives me the elasticity. We're going to work through an example a little bit on that. Before we do that example, I want to think about some different cases for elasticity of demand. So we're going to just put 3 little tiny graphs all side by side. Let's have one be that demand curve, one be some, we should do 4, but 1b that demand curve, 1b that demand curve, and the last one be perfectly horizontal. So 4 different cases. Elasticity of demand for this one's equal to, remember our extreme cases? What's at the 2 ends of the spectrums? 0 and an infinity. So it's a coin flip. Which one's that one? 0 or infinity? 0. Infinity? So if you're ever confused, you can go back and do the formula of percentage change in quantity over the percentage change in price. And for price, we'd have some number, but quantity, Q0 equals Q1. They're the same. So we got 0 divided by some number gives me 0. So that one's 0. This one would have the 0 on the bottom, which we can't do, but we can divide by something infinitely close to 0. Maybe I should do that little. I always like doing that anyway. So for this case, I don't think we can write this formula too many times anyway. We'd have some number for quantity, but no change in price. So we'd have some number divided by 0, which we can't do. But we can do some number, get as close to 0 as we want. So this is about as, this will be our one of our little tiny calculus lessons here. So we put this over 1 over $1 zillion, or not 1 zillion, but 1 over 1 zillion, so 1 zillionth. And we flip that, multiply times the numerator. At the end of the day, we can make it be as big as we want it to be, making this as small as we want it to be to make that denominator infinitely small. We make the expression infinitely big. So there's our 2 extremes, elasticity of 0, elasticity of infinity. We say that this is perfectly elastic. Perfectly elastic. This is perfectly inelastic. And then we got the in-betweeners. When it's real steep, we'd probably say that this is relatively inelastic. And this curve would probably be relatively elastic. So it's pretty flat, it's pretty steep if we start thinking about slopes that way. Yes?
Like I remember in principles we had the graph that had like the one line and it had like it divided or
Yep.
whatever, and then the middle point was like the 1.
Yep.
So like does that 1 come into play at all?
Yes. It comes into play here.
Like with the relatively inelastic be like less than 1?
No. So, okay, so good question, so I'm going to jump the gun to where my punchline's coming there here shortly. No, that's okay. So, yes, along a linear demand curve, the elasticity of demand changes. And it's split into those 2 segments. Somewhere along a downward sloping linear demand curve, the elasticity of demand is equal to 1. What did we call that? Unit elastic. Good. Unitary elastic or unit elastic. And where that special point is always the same along a downward sloping linear demand curve. If you take the intersection of where the demand curve meets the horizontal axis, cut it in half, bisect it, take the midpoint, go straight up, and hit the demand curve, that is that point. So why we call this relatively inelastic is because potentially over all relevant ranges of prices, the demand curve is inelastic all the way along it. So this demand curve, of course, imagine goes up to, whoops, get in trouble here, goes up to here, and this would be the elastic portion, This would be the inelastic portion. Same thing here. This demand curve comes out to here over some potentially somewhat irrelevant range of demand because the quantities are so huge. And we bisect it, go up to this point, and the elasticity of demand is equal to 1 at that point, the unitary elastic. Which brings up one other point here. The elasticity of demand technically is always negative. We express it as a positive because everybody knows that it's negative. What's the negative business again? What law does that come back to? So if you're calculating it, technically this would be a negative number, but we take the absolute value. We had that little trick of taking the absolute value. Why was that? Good. Quantity, be careful with the language, but quantity demanded. Price goes up, quantity demanded goes down. Price goes down, people buy more. Those are always moving in opposite directions. So if price goes up, quantity goes down, this is always a negative number. But we all know that, so we express it as a positive typically. And I don't know, I didn't look to see exactly how your author handles that here. Again, now that we're talking big time here, I'm sure it's mentioned somewhere in here, but anyway, it's always negative, so we generally talk about it as a positive. And you're supposed to know the basic law of demand. Price goes up, quantity goes down. Quantity demand goes down. Okay, anything else? All right, let's jump into that problem then. So this is a problem calculating elasticity. Why don't you guys start to work on it? You can work on it together. The demand for gym memberships in a small rural community is that function where Q is the number of monthly members, P is the monthly membership rate. So if we're following this logic, this is a good way to start. What should you do first with that equation? Change it to the inverse. Good. So go ahead and start doing that step. We're going to take that slope-intercept form, change it to the inverse demand curve so that it's in the format that we can use our formula. Something like looks like that. Now at this point, might not hurt. This is not really asked for, but maybe it wouldn't be a bad idea to graph that inverse demand curve. So we've got slope-intercept form. We've got 180. And we've got a rise over run of down 1 over 2. So down 1 over 2, down 1 over 2. Who knows what that looks like exactly? But we got something with the slope equal to negative 1/2. So what is part A asking for? Michael?
Price elasticity of demand. Price is $15 a month.
Okay, so what information do we need now?
We've got the slope of the inverse demand curve.
Okay.
One.
Okay.
And then we've got price. We just need to find the quantity at that same point, correct?
Okay, so we got the price at 50, and we need to figure out this.
Yeah, we can plug it into that original equation, and it's 260.
Good. Okay, so 260.
So take negative 1 over negative 1/2 times 50 over 260.
Okay. To calculate the elasticity. What number did you get? Oh, you haven't done it yet. Okay, go ahead and. Sounds like the right ropes. Anybody else? Everybody seeing that?
I got 460. What did you
So on your 260. Okay, you could go back into the original equation, might be a little bit easier. So you can always go back and forth. We're solving for the quantity, so when we start this off, try to see the path of least resistance for what you're trying to look for. So we created the inverse demand curve for some reasons. One was to get the slope so it fits into the elasticity. But we've got the regular demand function here. So if you're looking for the quantity of 260, we've got a membership price of 50, 50 times -2, you get 100, get our 260. So we're kind of plugging and chugging. On your exam problems, and so get in the habit of it now, you should be telling me a nice story that says substitute this into this problem. So you might start doing that little trick of, oh, if you want to do like equation star and equation double star, equation 1, equation 2, I don't care, whatever your kind of notation. But then you might say substitute, take the price of 50 and substitute into equation star. And we might be kind of overdoing it a little bit now, but I want to set the stage of kind of creating that logical framework of solving the problem and showing me where your work came from on the exam when I start to look at problems like this.
We just have it written out. Say instead of writing that out, we put Q equals 360 minus 2 times 50.
Yeah, something like that. Yep, that's fine too. Yep. Sometimes you'll find that this type of thing is easier, because a lot of times when we do this, it might not look quite like this. It'll be more like set star equal to double star or something like that. And that's just kind of a nice way to say, okay, where is that? And then start laying it out like Michael was saying. Doing it. Now we are not setting star equal to double star here. That was completely... 260. So is everybody there? Want to make sure we're all dialed in. Got any questions? Tell me as we. And then we're going to come back to that formula there.
And you wanted us to do the absolute value portion here as well?
It's going to shake out one way or the other. So you can let it drop. Again, at this point, hopefully we just know that it is going to be negative and express it as a positive.
Okay. I didn't know if you wanted us to just do that.
Yeah, I actually like seeing the negative, and that's the way the text shows it too. Just to, that helps when we come into cross price elasticity or income elasticities. Normal goods and inferior goods have different signs for the elasticity, so the sign really matters.
Yeah.
So it's good to kind of just don't just drop it arbitrarily. I'd say keep it through. Okay, so elasticity of demand equals 1 over. We got this formula to fall back onto for the slope of the inverse demand curve times our price and quantity, 50 and 260. And what did you guys come up with?
5/15.
How much?
5/13.
5/13. Everybody get that? What about decimal form? Usually we want to convert to a decimal form.
0.3846.
Huh?
0.3846.
0.3846. Did you guys get that too? John, what did you get? Yeah, did you do B too?
Yeah.
Okay. So 0.385 is what, 50/13ths or whatever, yes. So let's see, 260 negative. And if you worked ahead to B, we just picked a different point estimate of price equal to 100. What did quantity equal? 160. So it's just kind of another run through the numbers. And elasticity of demand here equaled
5/4 or 1.25.
0.125 or 1.25. All right, and does that make sense with what we have learned before with elasticities? Is the number supposed to be getting smaller or bigger? We can kind of double check our logic here. So we're taking a point estimate there and a point estimate there. And we're saying that the elasticity was 0.385 here and 1.25 here. Which number is more elastic? The bigger one or the smaller one? And now we got that negative thing to boggle our minds with too. 1.25 is more elastic. Good. So that's more elastic. If we go back to the definition of a 1% change, a 1% increase in price leads to a 1.25% decrease, as opposed to a 1% change leading to a 0.38% decrease. So we can kind of start thinking about the interpretation difference there. It also means that we crossed over 1 somewhere in the middle. So again, I didn't draw this to scale, but presumably the midpoint's somewhere in between here. And so as we move upward along a linear demand curve, the elasticity of demand in absolute value gets bigger. So as you approach this endpoint, it gets close to infinity. Down here, it gets to 0.
Does elasticity, does it grow at an exponential rate, or does it grow at an So like, would there be?
I think it's non-linear, but I'm not sure. That's probably a nice little proof that could be done on that, but I think it's got to be nonlinear because you're approaching infinity at this endpoint. So
Okay.
I'm pretty
I was
sure
just trying to
the
figure
slope
out-
is constant. The elasticity is in some nonlinear form, yes, or nonlinear relationship.
It's-
Okay, so let me tie that back then to the big picture, and I'm going to work it right away back to my favorite model. My stacked graph. Well, it's not really mine. I didn't invent it, but I just like it. So over here, on the bottom graph, we're going to measure total revenue. Or you can also think of it as total expenditure or total spending that you're doing. I'll come back to that in a second. Upstairs is the demand curve. So if you take the midpoint idea here, roughly eyeball the midpoint, go straight up, that reflects the unitary elastic. I like to just draw my absolute values around there. I don't think this textbook does that. But over this range of demand, the elasticity in absolute value is less than 1. And over this range, the elasticity of demand is greater than 1. So this is the inelastic range. This is the elastic range. And here is unit elastic or unitary elastic. It's equal to 1. Let you guys get caught up with that. So I'm just going to make up a number here, but if we have $50 worth of a price, and we're buying 30 units at $50, I'm just arbitrarily picking the point where it's unitary elastic. How much money are we spending that day at Target? What's our total spending? 30 items at $50 a pop, $1,500. So downstairs here in this graph, that corresponds to a point where spending is $1,500. The P times the Q is here. The rest of the points along this particular graph would look like this. At a price of 0, quantity 0. At a price of, I'm sorry, I didn't mean that, an infinitely high price, nobody's going to buy any. So an infinitely high price, or this price actually, since it's our intercept, people, that's called the choke price, by the way. Quantity 0, so expenditure 0. At this low price, we're giving it away for free, and that many people want it at a price of 0. And this is a humped looking curve function that looks like this. On a linear demand curve, that total revenue function or total expenditure function looks like this.
So choke price is where nobody will buy it for.
Yeah, so
infinite
this,
price.
let's go ahead and put that on here. This is called the choke price. Same thing applies to kind of choking off the market at that price. Nobody wants it. The quantity demanded is 0 at the choke price. And so the lesson learned here is that if you're operating in the inelastic portion of the demand, a price increase leads to a revenue increase. However, if you're operating in the elastic range, that same price increase of whatever amount, $2 or something, leads to a fall in total revenues. So that was the neat thing. So last thing I'd probably put on here would be moving from point A to B moves you along the revenue function from A prime to B prime. It increases revenues. But moving from point C to point D, an increase in price directly corresponds with a decrease in spending by the consumer, or revenues therefore from the firm. So this has a lot of insight that we'll talk about throughout the book, actually, when we get to the pricing chapter later. This is one of my favorites. Have that memorized. There's a lot of insight in that one.
A prime B up on the above graph.
What's that?
Isn't, I'm just thinking as far as calculus, wouldn't the above graph be the prime graph?
Oh, well,
Yeah.
you're actually taking, if you want to get into the calculus part, down here, this is a total revenue function. The marginal revenue would be a prime taking the first derivative off of the change down here. A very small change.
Whatever. We're not doing calculus.
We're not doing calculus, yeah. So, but I am going to at least mention things like that as we go through. So, okay, let's call it a day. Have a good weekend, and I guess we're off till Wednesday. Kate will be entertaining us with the Ku Klux Klan talk and real estate agents and any wild connections those two groups might have. So hopefully you'll have your textbooks. I don't know, was yours en route still?
Mine's in the
Or if you
post
got-
office in Ottawa right now.
So next week, your first homework set will be due. A week from today, chapter 2, the starred problems in the back of the chapters. Okay? So next week, Friday, the starred problems. There's 6 starred problems at the back of chapter 2. That's your first homework problems to have done.
Due Monday?
That's due a week from today.
Oh,
On Friday. Yep, a week from today on Friday.
have a good weekend.
Yep, you too. And you will turn those in just by hand. Those exercises just turn in by hand.
And then I'll get it back to you. Robert.
Yeah, if you need me to run, I could go downstairs right now and run through the copy machine if you guys have copy codes or whatever that uses up your paper count. Or, oh, you got class, okay.
Where can I find like more